I'm going to be talking about a paper that was also published in Structural Dynamics. It's called Microfluidic Sorting of Protein Nanocrystals by Size for X-ray Free Electron Laser Diffraction. And a lot of the authors are also our buddies in the BioXFEL STC. So the first question we have to start out with is, why would you want to sort these protein nanocrystals by size? And it comes with, comes with a problem you have when making crystals for these serial femtosecond crystallography experiments, which is that it's very difficult to get crystals that are all in the same size range. And sometimes smaller crystals are better. So for example, maybe you have a protein where the mosaic block is kind of big. You want the crystals to be small so that the crystals aren't prone to long-range disorder. So having these crystals be of a narrow size range is really important. And it's hard to do if you just have a batch of crystals. So what this paper talks about is a device, a microfluidic sorting device that's fabricated from PDMS. And the way it works is that you have your crystal solution, your unfiltered solution comes in from the left side of the device into a sort of constricted area across which you apply an kind of an inhomogeneous electric field. Now, when we do this, you end up with an electric field gradient which exerts a repulsive force on the crystal particles. And it turns out it's set up so that the force on the particles is proportional to the radius cubed. That means bigger crystals experience quite a lot of repulsion and smaller crystals don't experience very much at all. So these larger crystals are kind of flung into this output channel here and go as far away from the field as they can. And the small particles don't care as much. They can kind of migrate down these small channels close to the field. So the bottom line is they flow the unsorted crystals in from the left. The large crystals continue straight and out to the right, and the small crystals migrate up these side flanges here. So the idea is that if you were to take the solution out of these two side channels, you would have only small crystals and none of the big stuff. So let's see how this works. They did a bunch of characterization of the sorted and unsorted material. The first technique they used is dynamic light scattering. So in their unsorted crystals, before going through the device, there is a large size distribution. There's everything from about 200 nanometers up to 20 microns. That's pretty big. And then they went through and they harvested some crystals from the side channel. So these should be the sorted small crystals. And sure enough, the size distribution is significantly narrower. So these guys are, you know, in the 200 nanometer up to about 600 nanometer range. So looks pretty good. They also did some characterization by nanosite, which is nice because you can actually visualize the particles. So this is their sorted sample, and as you can see, they're all quite small. And again, kind of agreeing with what we saw from the DLS, size range is smaller than about 600 nanometers. So, so the device looks like it's pretty efficient at getting rid of large particles. But the next question you might ask is, what happens to the crystals when they go through there? Are they still intact? So they did a couple of crystal quality checks. The first is looking at the sonic signal. So sonic gives a signal if there's chiral crystals in your sample, but not just protein molecules or amorphous aggregates. So these are some things that came out of the sorted channel, and as you can see, they do have sonic signals, so that suggests they're crystals. They also checked these guys with TEM. So on the top row here, I've got some TEM images of unsorted crystals. On the bottom are the sorted. And as you can see, the sorted crystals, their lattice structure still looks quite good. Everything looks regularly spaced. So we're able to sort things here. And it's really quite amazing because the crystals that come out of this huge electric field gradient are still intact and still have good lattice structure. So one thing that's really interesting to us XFEL people is how do these things diffract in the XFEL beam? And they've tried this. They ran their sorted crystals through the beam, and they were able to get sharp diffraction spots down to about 4 angstrom resolution from these really tiny crystals, which is really quite amazing. And the hit rate was kind of low, but the crystals are tiny. So it's possible that if they concentrated the crystals more, or potentially when future brighter XFEL sources come online, we could see even better results than this. So some applications. One application of this technique is the narrower size range of crystals this produces would enable you to see if the crystal quality does depend on a function of size easier, and would enable techniques like high-intensity radiation damage-induced phasing, where the whole crystal really needs to be exposed to the beam in order for the technique to work. So it also, one thing that's cool is it enables a more efficient use of these protein crystals. And so they've done some simulations of diffraction patterns and have actually shown that from the smaller crystals, you get a higher degree of reliability from the merged reflections. So it's possible that if you sort these crystals and you use only the small ones, then you break down the larger crystals and resort them. You could use only these small crystals, and that could lead to a reduction in sample volume by about 3,000 times, which is pretty nice. So to summarize the paper, these guys have built this cool microfluidic device that uses electric field gradients to sort crystals based on size. The sorted crystals do have a narrow size distribution and also good crystal lattices, so they're not torn apart during the sorting. Additionally, their experiments and simulations suggest that the small sorted crystals actually, they give high quality diffraction patterns from less protein. So that all sounds like a really good thing. So I guess that's my presentation. Thank you all for listening. And if you have questions, I can try to answer.
Okay, thank you, Andrea. Any questions? No? Bobby or Austin, do you have any questions?
No questions. It was really well done.
Thanks.
Thanks for the praise.
No? No other questions? Okay. Well, thank you to both.